Okay, guys, let's start chapter 1. It's all about motion. You kind of have an idea of what motion is, but we're going to take it way more in depth than what you currently know. And hopefully we'll learn a lot from this chapter. I think we will. So let's get to it. Follow along with the guided notes as we go through these slides. Fill in any missing information. Okay, we're going to start off by talking about the difference between these two words. Okay, we're going to talk about scalars, and we're going to talk about vectors. Have you guys seen that, what's that show, the little yellow men, the Minions?
Minions!
What's this first one? What are they called?
Bananas.
Despicable Me. Is it Despicable Me? Yeah. Have you guys seen that part on Despicable Me where he talks about vectors? I've never seen the show, but I've heard it from other students. Yeah, he tells you what a vector is. What is a vector? You guys remember?
I don't. Like the vectors you learn in math class?
Yeah, sort of.
Sort of?
No, have you seen Despicable Me? Never mind. Let's move on. Okay. Scalars. Let's move on. Scalars. Hey. Scalars are quantities. So it's a quantity that shows magnitude only. So it's magnitude only, which means an amount. So it's a quantity that just shows amount. Here's an example of a scalar, like mass. Like how many grams of mass does it have? It's just a number. Time, it's 1050. Just a number. Money, they have $20. Just a number. And distance, it's 10 kilometers. Just a number. So those are scalar quantities. Just a number. Let's contrast that to what a vector is. Vectors are quantities that show magnitude and direction. So not only is it a number, that's what a magnitude is, not only is it a number, but it's got to have and give direction. So here's some vector quantities. A force, like if I push on a box with 5 newtons of force to the right, I'm giving you a magnitude and a direction. Weight. Which way? So I weigh 65 kilograms. How does that show direction? Which way is weight going? Down with gravity. So it's giving you a direction as well. Velocity has to have a number and a direction to it. Same with acceleration and displacement, which we'll talk about here in a second. So, the thing to take away from this slide, scalars just show a number, a magnitude. Vectors have a magnitude and a direction. Let's go through practice problem number 1 and see if we can figure this out. It says, which statement below describes a vector quantity? So there we go. Not a scalar. We want to know which one's a vector quantity. Let's go through each one of these. A race car moving at 110 miles per hour. Which one is that, scalar or vector? Does that show direction? No, so it's a scalar. A is a scalar. It just has a number. What about B? A turtle strolling at 200 centimeters per minute. He's just strolling. Trevor, he's just strolling. Is that a scalar or a vector? Trevor Burton.
That is scalar.
Scalar. Good job.
Thank you.
Part C. An SUV moving at 40 kilometers per hour east. Scalar or vector, guys?
Vector.
That's a vector. So there's our answer. Yeah, not only does it have a magnitude of 40 kilometers per hour, it has a vector. It has a direction east. So it is a vector. Okay, in physics, we use the coordinate system to plot position. The coordinate system is, it has a y-axis up and down, and it's got an x-axis left and right. It's called the coordinate system because it has 4 coordinates. This is coordinate number 1. This is coordinate number 2, 3, and 4. Let's talk about these coordinates for a second. Let's talk about quadrant number 1. Is x going to be positive or negative in this quadrant?
Positive.
X is positive. What about y? Y is going to be what? Do we have to go up? So y is going to be positive. Yeah, x is moving to the right and y is going up. They're both positive. Let's talk about 2. X is going to be what here, guys? Positive or negative value? X is going to be negative because we had to move to the left, which is negative. Y is going to be what here? Positive. We have to go up, so it's positive. Okay? Let's go to quadrant number 3. X is what here? Negative. And y is also negative. Yeah, we had to go left, which makes x negative, and we had to go down, which makes y negative. Let's go to quadrant number 4. X is what here, guys? Positive, because we went to the right. And y is negative, because we had to go down. So anyway, when we plot position in physics, we're going to use the coordinate system. Just a little introduction to that. Position can either be positive or negative. Position can either be positive or negative. Now that might be a little bit new to you guys. We're going to explain what that means here in a second. The directions on this coordinate system are up is north. So up here, north. To the right, we're going to call that east. Down is south. So south down here. And to the left is west. And what makes this room such a great room to learn physics in is when we look straight ahead, we're looking north. When you look right, which way is that, Dawson?
East.
East. Behind us is south, and to the left, if we look left, is west. Okay, now it says that position can either be positive or negative. When we go to the right in physics, that's positive. So east is going to be positive or negative? If we're going east, we're going a positive direction. What if we go west?
Negative.
That's going to be a negative direction. What if we go north? Positive or negative? Positive. What if we go south or down? That's negative. Yeah. So can I tell you which way something's going by positive or negative? Could I also say it's going to the right? Would that be positive or negative? Positive. If it's going to the left, it's negative. And so that's kind of how it works. A little bit new. We'll get used to it, though. Up. Okay, yeah. So up to the north, so up here, and to the east, this is east, these guys are positive. If you go down, which is south, and left, which is west, we're talking about negative values. It's a negative position. Okay. Were you supposed to draw? You're supposed to, in the guided notes, draw a coordinate system and label the following parts. So let's make sure we do that. X-axis. X-axis is this one. It runs left and right. Y-axis is the one that moves or runs up and down. East, we've labeled it. North, we've got it labeled. West and south are also labeled. Positive X and Y quadrants. We did that earlier. This is positive X, positive Y. So positive and positive. What about this one? Negative X and positive Y. What about quadrant 3? Negative X and negative Y. Quadrant 4, positive X, but negative Y. Okay, so you've got to have that labeled in that spot on your guided notes. Okay, let's talk about the second thing that we wanted to learn today. We're going to talk about distance and displacement a lot for the next little while. They're very different, so let's learn how they're different. Okay, distance is a scalar quantity, which means it's a measurement of total distance traveled. It's just a number. It doesn't tell us direction. It just tells us how much distance we have traveled. What is your total distance traveled? So remember, Distance is a scalar, just concerned about a number there. So, how do you find distance? You simply add up all the distances traveled, does not mention direction. Okay, let's contrast that to the second word up here, displacement. Displacement, like it says, is a vector quantity. Displacement is the difference between final and initial positions. It's the difference between the final and initial positions. Now, I didn't put this on the notes, but I want you to write this on your book somewhere. Okay? In physics, you're going to see this symbol a lot. It's the Greek letter delta. What does it mean in physics? Change. Good. So put this on your margin of your book, or the top of your book, or the bottom somewhere. When you see that in a physics book, that means change. Another way of saying change, and I want you to write this as well, because you're going to see it a lot, is final minus initial. Okay, so when we want to figure out the change in something, like change in speed, for example, we'll take the final speed minus its initial speed, and that will give us its change. Okay, so let's talk about how to find displacement. It says here that change in d, which is change in displacement, is equal to p sub f minus p sub I, where p sub f is the final position. So this p means position, and this subscript f means the final position. Minus position initial. So final minus initial. Again, we're seeing that triangle. It's always going to be final minus initial. And that's how you will know it's displacement. We're going to go through some example problems, some practice problems here, and we'll get this down. Okay, this is just a good kind of a, what do you call these things? Animation, I guess. It's a good animation that kind of shows you visually the difference between distance in blue and displacement in red. Now, if I asked you to find this bug's distance, how would you find the distance of this bug? Cole, Benson, how would you find the distance that this bug traveled? Which line, the red or blue? The blue line, yeah. You just measure how long this blue line is, and that will give us distance. Want it, guys? Yep. Sure. Displacement, now, look how displacement is different. When he finally gets to his final spot, point B, his displacement is a straight line. It's just, remember, displacement is equal to position final minus position initial. So we take his final position, subtract off the initial position, and we'll have this straight line between them. So, will displacement always be a straight line? Will displacement always be a straight line? Yeah, it's just the difference between 2 points. It's going to be a straight line. Now, will distance always be a straight line? No. Okay. All right, measuring distance and displacement. How do we measure it? Well, the SI base unit for measuring distance and displacement is the meter. Something different for us. We're not measuring it in feet or miles. We're always going to measure it in meters, which is always abbreviated with a lowercase m. So that will mean meter whenever you see it. Okay, let's go to practice problem number 2. It has a couple of parts. Part A, which color of line represents the distance that you walked? Let's look at this diagram for a second. You're starting here at home, and you're going to go to the school up here. So which color of line represents the distance that you had to walk? Yellow. Yeah. You obviously can't cut straight through a block. You're going to follow the streets. And so this is your distance. You add up the length of each one of those segments, and you're going to have your distance. Now, obviously, which color of line represents the displacement? The red line. It's going to be a straight line to to your final position. That is your displacement. Okay. When you say, if you figured out how long this red line was, say it was, let's say it was 2,000 meters. What would you also need to add in order to make it a displacement?
Northeast.
A direction, good. You would have to add, he went north and he also went to the right, which is east. So you would have to add his direction. Good job. Okay, practice problem number 3. Let's see if we really understand it. This is a good question, so pay attention. It says, find the distance traveled in going from the math classroom to the library and then to the physics room. Okay, so we're starting at the math classroom. We're starting here. We're going to go to the library, and then we're going to head back to the physics room. Okay, here's your scale at the bottom. So be looking down here for the values. We started at the math classroom. How long was it? What was the distance to the library? 8 meters. So this segment took 8 meters. What was the distance from the library back to the physics classroom? We're going from 0 back to 5, so that's 5 meters, right? So what was his total distance? 13 meters. Okay? Does that tell us anything about direction? Nope. He just walked a total of 13 meters. That's all it tells us. That is all it tells us. Okay, now that I've wrote all over B, let me read it. It says, what is the displacement? Okay, displacement. Now, there's a couple ways to think about it. I always like to go back to the equation. Okay? Displacement is equal to position. You guys help me out. Position what? Final. What goes here? Minus position initial. Now let's just plug in the values for those variables and see if we can't figure this out. What was his position final? Yeah, we ended up in the physics classroom right here, and if you look down, that's 5. So 5 meters was his position final. Minus, what was the position initial? Yeah, initially we started at 8 meters. Well, what's 5 minus 8? That's a negative 3. Negative 3 what? We always got to include the units. A negative 3 meters. Okay? Well, how does somebody walk a negative 3 meters? Is that even possible? Is it possible to walk a negative 3 meters? So here's what I really want you to learn right now. The sign is telling us what? Direction. Sign tells us direction. Please write that somewhere on your book. The sign tells direction. Okay? I like to do it through the equation and get a minus 3 meters. To me, that negative sign just tells me that he walked which way? Right or left? He ended up left of where he started from. And we can look here. He started at the math classroom. He ended up 3 meters to the left. Could you also have just looked at it and said 3 meters left? Yeah. But you would say 3 meters. Could I just circle 3 meters? To the left. Would that also be his displacement?
Yes.
Sure. Could you also write 3 meters west? Sure. Okay. But I want to use this notation. Negative 3 meters. That tells me that he ended up 3 meters to the left. Okay. Sign tells direction. Let's go to practice problem number 4. It's also got a couple of parts. So let's look at this diagram. It's of a marble. It rolls from P1 to P2. So like it says here, P1 to P2, and then back to P3. So it's going to here, and then back. Let's answer the questions. A, what distance has the marble traveled from P1 to P3? Let's do P1 to P2 first. What was that distance here? We're starting at 3 and going to 7, so yeah, that's 1, 2, 3, 4. How much distance did it take to go from the far right side clear over here to the left? 7. So if we're going to find the total distance, what is it going to be? 4 plus 7. What is that, guys? 11. Did it give us a unit? No. So I'm just going to say it was meters. Okay. That's his total distance traveled, 11 meters. Now you guys see if you can tell me its displacement. Take a second, see if you can get it right. Okay, I'm going to solve it with the equation method, and you can look at it and you can see. What was the final position? Let's plug in a value here. That's 0. So we've got 0 minus, what was the initial position? 3. What is 0 minus 3, guys? Minus 3. And we're talking about meters, so I'm going to circle that. Can something really go at minus 3 meters? Well, no. What does the sign tell us here? 3 meters to the left. That this marble ended up 3 meters to the left. Okay, good job. How many of you guys got that right? Good. Okay, practice problem number 5. It says that 2 bicyclists travel from house 1 to house 2 as seen in the figure below. Path A is a straight and path B is a curved path. Which path has greater displacement? Justin, which one has greater displacement? B? So the curved path? So you're saying this curved path has greater displacement? Or is this a trick question?
Displacement's the same.
Yeah. This is kind of a trick question, right? Displacement is the same for both of them. What's different, though? Distance. Yeah, the curved one, this one has more distance, but you can see that the displacement is the same. Yeah, kind of a trick question. The same. Okay, I'm going to pause the video for a second. If you're watching the video, you've learned enough to do the first worksheet in the student workbook. So pause the video for a second. We're going to do distance versus displacement worksheet in the workbook, and then we'll get back to the video in a second.